Good afternoon, everyone. So today, as a part of our weekly seminar, we have Dr. Mohammad Ramiz Aktar. Ramiz did his PhD from IIT Guwahati in 2019. He is a postdoctoral fellow at the Department of Astronomy in Xiamen University in China. And as you know, most of you know that currently he is visiting Aries for last couple of months. So he will be talking about his ongoing work. And welcome, Ramiz. You can start your presentation. So I'll give you a reminder 5 minutes before your time.
Yeah, thank you, Shubhendra. Okay, so good afternoon all. So, and welcome you all in this seminar. So I'll be talking about basically these spiral shocks in accretion disks with mass outflow in binary. And some of the application I will show, and mainly the accreting in the application in the accreting white dwarf. And this work is mainly based on theoretical modeling, but I will give some perspective how we can apply this theoretical model into some observational sources. So this work has been done in collaboration with Professor Lee and Liu in Department of Astronomy at Xiamen University. So this is basically outline of my talk. So first I will briefly describe what are the spiral shocks, why spiral shocks are forming in the first place. And then I will briefly describe the model description and mathematical formation, which is very much needed to describe our model. And finally, I will describe some results and discussion and some application that I will describe. And then finally, I will describe some future perspective based on our model calculation. So as we know, what are the compact objects? So compact objects is basically the object in which the mass and the size ratio is much greater than unity. So that means compact object is very highly gravitational system. So it can pull its nearby matters due to this huge gravitational force, and this process is known as accretion. And as we know, in the universe, no matter is static. So due to this accretion process, the accreting matter is also has some.
Ramizji, your voice is quite low.
Okay. Yeah, it suddenly drops down. So
now it's okay.
No, it's the same. It's not. I mean, before it was good. I mean, when you were.
Now.
Yeah, now it's good.
Yeah. So accreting matter has some also finite angular momentum. So
again it drops.
Okay. I don't know what is happening.
You increase too much, then your background noise is coming some.
Okay. Okay. Let me just check. It's okay now.
Yeah.
So maybe some technical difficulties.
Yeah.
So we know that the accreting matter has some angular momentum. So
same again it reduced. So probably you can speak a little bit louder and continue, because I think there's some technical problem.
Now it's okay, Shwanda?
Yeah, it suddenly is dropping down. And
I don't know what is happening. Okay, maybe mouthpiece. I should bring the mouthpiece very little closer. Yeah.
Okay.
Now it's okay.
Yeah.
So we know the accreting matters have some angular momentum. So due to this angular momentum, it forms a disk around the compact object due to this centrifugal force, because the accreting matter has some angular momentum. So this is basically known as the accretion disks. And this is an artistic impression of accretion disks in a binary system. So the compact object is sitting center of this accretion disk, and this is the companion star, and this is one kind of Roche overflow through this first Lagrangian point, and there will be jet or maybe some wind throughout the disk from the accretion disks. So we know that in astrophysical system, most of the system are in binary form. So this is an schematic diagram of binaries. So first one is basically the detached binary system, where we can see the two stars. They are completely separated from one another, and neither of these star fill the Roche lobe in this system. So, and also these compact objects are roughly spherical in shape. And this is basically the semi-detached binary, where one star can fill the other Roche lobe, and one star, due to this compact present of this compact object, this star has to be distorted due to the mass flow through this inner Lagrangian point. And this is basically the contact binary, where both the star fill their Roche lobe and touch the first Lagrangian points. And this type of system, the merging may occurs. So we are interested in this
Hello? I cannot hear you. Hello, Suvendu.
Looks like internet has gone down in Aries. I don't know.
No, I'm in Haldwani. It is not working here. I cannot hear.
Yes, I think it was disconnected also for few moments. I'm in Aries, so
Yeah, some problem with the network in the campus.
yeah, always the problem. In the morning, it was
Yeah.
also problem, but
Monkeys might be playing with some antenna or whatever.
but in the morning, I mean, it was fluctuating a lot. Anyway, where is he now?
Yeah. Tomorrow, in 2 days, election counting is coming. So fluctuation is happening.
Yeah, there is fluctuation in time also now in election.
Yeah.
Instead of 10, now it is 2:30.
What happened to speaker? Rest everybody joined. Speaker agent.
Let me. Can anyone contact him if he has his number, or if he has numbers? I don't have phone number probably. I think I was disconnected also for 9 Aries. So
This talk is recorded as well as streaming live on YouTube. So mind your words, please.
yeah, so where is Ramiz?
I think we should stop YouTube recording.
This was supposed to be an Aries internal talk because Mr. Ramiz Aktar, he's a visitor of Aries. It is not a like invited talk or kind of.
No, yeah, why we telecast all the talks in
No,
Zoom?
not all that. Only when the speaker is from outside Aries and is invited to give a seminar or a colloquium, that type only should be live stream.
Exactly. So this information should go to
Yeah,
Javed.
this is supposed to be an internal talk.
Yeah. So
because this is the work he's showing, it should be based on the work he has done during his visit.
So I think convener of the seminars to inform Javed.
Very, I think it's not. I mean, let's talk separately because
we can discuss this later. No problem.
Because the presentation he is giving is the talk he said, that is the reference he mentioned. It was previously, right? I mean, if you check the first slide of his presentation, so it's not that work he done here. So
okay.
Yeah, so let's not.
But anyway, first let us find out what happened to him, where he is.
Yeah, I'm trying to call him and we'll see. So it seems like he is having the internet connection issue, and he's trying to figure out. So let's wait.
He, make his phone hotspot.
Here, I think mobile internet also is not good. So
Mobile is even worse. Right?
yeah, mobile is very. Yeah, is rare. You can rarely connect it, and even also it's difficult to call him also because it's disconnecting.
Oh, okay.
So Javed, what was the problem with the internet?
Yeah, Subhendu-da.
Yes.
Yeah. So
Yeah.
there is power cut in the PDF. Yeah. So that's
Okay.
so now it's audible, right?
Yes, I can hear you, but also fainter, but not. If you can speak louder.
Yeah. Now it's okay.
Yes, not that much. Yeah, reduce little bit because it's background. Yeah, now you go ahead.
Okay. Sorry for that. Yeah. So I am here, right? What is shock?
Yes.
Yeah. So now, why this shock is forming in the first place? So here I have plotted one comparison, simplistic plot. So here I compare the gravitational force with the centrifugal force. So this is basically the centrifugal force. This is the gravitational force. This is basically we can see near to the compact object. So there is a comparable region where these two forces are competing with each other. So in this kind of situation, in this region, this very near to the compact objects, the inflowing matter slows down due to this repulsive centrifugal force, and there will be density will be increased, and due to this here. So what are the physical conditions for shock transition? So basically we need the mass conservation across the shock that has to be conserved. Also the momentum conservation, where this P is basically the gas flow and V is the radial velocity of the matter. And here also the energy has to be conserved across the shock. So here E is basically the internal energy, P is the gas pressure, and this is the kinetic energy term. So before going into the further, so I want to show one animation. So it is showing, right? So
Yes.
yeah. So here basically we inject matter from outer boundary. This is the temperature variation. This is the density variation. So here we can see, and this black dot is basically the sonic point. This is the outer sonic point. This is the inner sonic point. And we can see if we inject matter from the outer boundary, it can crosses the sonic point and become supersonic. And if the shock conditions are satisfied there, so there will be a discontinuous transition of flow variables from the supersonic branch to the subsonic branch. And this is basically the shock formation region. This is also the temperature. We can see at the shock, temperature is rising. Also the density that I already mentioned earlier. So now, what is this? So already we know what is shock in general. So what is a spiral shock? So first we have to understand why this spiral arm are forming around the in the accretion disks around compact objects. So this is basically for presence of secondary star near to the compact object, and also some massive object or the such as the globular cluster or the molecular cloud or another black hole or another compact object which is passing very near to the compact object. So basically this spiral arm are forming due to the tidal force, due to the presence of this object, okay, or the secondary star. So why? So what is a spiral shock? So basically, if there is a spiral arm in the accretion disks, so the outer part of this spiral arm are attracted. Okay, so due to the presence of the secondary star or the massive object near to the compact object, also the inner parts feels the gravitational force by the compact object. So there will be also the infilling matter slows down, and that can trigger the spiral shocks. Okay, so here I have shown one simulation results around black hole. This is where we can see this is basically the density plot, the surface density of the accretion accreting matter. So here we can see the spiral arms are forming here. So this outer part is really attracted by the tidal force, and inner part is attracted by the gravity of this black hole. So here we can really the spiral arm are forming, and in this region, if the tidal force is comparable to the gravity force, so there may be spiral shocks happens. Okay, so here also I want to mention some important parameter here. So in this spiral arm, so this is basically the direction of this spiral arm. This is the tangent of the spiral arm, and this is the azimuthal direction. So angle between this azimuthal direction and the spiral arm, this is basically known as the pitch angle of the spiral arm. So this is also a very important parameter for our analysis. I will come back to that. So another important aspect is that we know that one of the fundamental question in the accretion disk physics is how the angular momentum is transported in the disk. Okay, so there are some various model. So first, Sakura Tsunoyama 1973, they proposed the alpha disk model. This is very popular model, in which they explain that the transport of angular momentum is happened due to the viscosity. And this viscosity, the origin of this viscosity is not clear yet. And also another proposed model is there, which is the magnetorotation, that is popularly known as the MRI. It is triggered by the small scale tangle magnetic field in the accretion disks. This is proposed by also, there are some problems that we don't know the structure of magnetic field in the accretion disks. So this is also an debatable subject, this the origin of viscosity as well as the structure of the magnetic field. But on the other hand, the effective transport mechanism of angular momentum is basically the spiral. There is also a if in the accretion disk there is a spiral shock, there will be a dissipation of angular momentum, and this angular momentum can transport the of angular momentum throughout the disk. So here I have mentioned what is the amount of dissipation of angular momentum due to the spiral shock in the accretion disk. So post-shock azimuthal velocity to the pre-shock azimuthal velocity. This is basically the rate of change of rate of dissipation of angular momentum in the disk. So now describe our model description and mathematical formulation. So before going to the mathematics, I want to show the schematic diagram of Roche overflow. So this is basically the primary star sitting here, M1, and this is the secondary star. And the this mass of the secondary star flowing through this fast Lagrangian and it form a accretion disk. And you can see that it will circulate around this primary star and finally fall into the reach to the surface of this primary star. And you can see there are some circular regions in the accretion disks. Not all the radial distance it can form the spiral shocks. I will come back to that. But there are if the spiral shocks condition are satisfied in the accretion disks, there might be spiral shock present in the basically basically the binary angular velocity, and Q is basically the binary mass ratio, which is defined as the ratio of the secondary mass to the primary mass. And Q and omega, it is very important parameter for our analysis, which is known as the binary parameters. So now let's discuss our model assumption. So here we consider basically steady, where the time derivative is not present here. And we also consider the adiabatic and also non-axisymmetric. So there will be a term delta phi present in the accretion flow. And where we consider a compact star and in a binary system. And here we consider the all the possible influences from binary by adopting this Roche potential, also the Coriolis forces equation. And for the solution purpose, we adopt the self-similar approach already proposed by Scoot 1987 and Chakraborty 1990. And in this calculation, we consider the rotating frame. So we calculate this self-similar approach point-wise, means in the radial variation. So we name it this approach as point-wise self-similar approach. And here we also use the unit system like this, where A is basically, capital A is basically the separation of this two star, this primary and the secondary. So first, I want to describe the Roche potential. So we all know that this is basically the Roche potential. It is combined of this gravitational potential. This two term is basically from the gravitational term, and this is the centrifugal term. And there are the other variable I have mentioned their relation here, and also the Coriolis forces. We can define the Coriolis forces like this, where this ER and E phi is basically the unit vector along radial direction and the azimuthal direction. So these are the conservation equation for binary system. So first we need radial momentum conservation equation. So this is basically the radial momentum conservation, where VR is radial velocity, V phi is azimuthal velocity, R is the radial distance, and P is the, already I mentioned, gas pressure, the rho density. And this is basically coming from the Coriolis forces. This is the Roche potential or the Roche force. And this is the azimuthal momentum. And also basically the disk height. And the vertical, here also we assume that the disk is vertically stable or hydrostatic equilibrium in the vertical direction. So here we also mentioned the vertical pressure balance equation, where G is basically the gravity force. So now what is the self-similar approach? So here we basically convert, so these equations are in cylindrical coordinate. I forgot to mention. So here we transform the cylindrical coordinate system at equatorial plane to the spiral coordinate. So here we transform these coordinates like this, and also we defined a variable which is or the coordinate which is known as the spiral coordinate like this, where beta is basically defined as this, where this capital B is tan theta, where theta is the pitch angle for our model. Okay, and this is the self-similar relation. If we use this relation, we can this conservative equation, we can get the dimension. Okay. So briefly, I want to mention what is the method that we are using here. So basically, if we use this self-similar relation or in our conservative equation, so we will obtain the dimensional equation for Q1, Q2, and Q3. So this is basically the radial velocity at the spiral coordinate. This is the azimuthal velocity in the spiral coordinate, and Q3 is basically the sound speed at the spiral coordinate. Okay, so here we for this solution we need flow parameters. So here we fix the flow parameter to solve this equation, that is theta, and also the adiabatic index, and also the binary parameter I already mentioned. We need this binary parameter to get the solution, and additionally we need to supply the number of shocks. So in our model we don't know what is the number of shocks in our model. So already Sprout et al. 87, they proposed that, or theoretically they showed that the number of shocks, spiral shocks, may ranges from 1 to infinity. So here we supply this number of shocks for our convenience to calculate the solution topology. Okay. So also, we assume that the mass from the disk is ejected due to the shock compression, or the due to the spiral shocks, there will be shock compression and the velocity, temperature gradient at that shock position, and it can drive some accreting matter from the disk as mass is calculated disk, and the outflow rate we can calculate using this ratio of the mass outflow rate to the mass inflow rate. And here also the Mach number is defined as the velocity perpendicular to the shock, spiral shock, to the sound speed. So now let's discuss about some relation solution topology. So here initially we know all the flow parameters cannot form the spiral shocks. Okay. So first we investigate the solution topology where there is no spiral shocks. So the, here I showed two solutions where we plot the Mach number in terms of the spiral coordinate. So this is basically the sonic point, saddle type sonic point. So this upper panel is for lower pitch angle. This is for higher pitch angle. So we can see these two solutions. Also, if we change the flow parameter accordingly, or the binary parameter, we can have the spiral shock in the flow. So here we choose the number of shock is 1. So that means in this type of flow, there will be only one go to the reach to the primary star surface, and this is for number of shock is 4. So here we can see the initially the accretion flow is subsonic, and it passes a sonic point, becomes supersonic, and if the spiral shocks condition are satisfied, there will be a discontinuous transition of flow variable from supersonic branch to the subsonic branch, and again it becomes due to the shock transition, it becomes subsonic, and again it can passes another sonic point to become supersonic and reach to the primary star. So this is basically the thing happening, and also similarly from here we can see for number of shock, its number of shock is transition in the accretion flow. So now let me describe one solution topology in terms of the radial variation. So that means, let me go back to this diagram. So here I have shown the various circular orbit here in the radial direction. So in these cases, you can see not all the radial position have the spiral shocks. So here I want to show that. So here we also plot the Mach number in terms of the spiral coordinate for various radial variation. So you can see it is very near to the primary star. So there is no shock, spiral shock. If we increase the radial distance, we can see there is a 2 shock is forming in the accretion flow. Also, if we increase slightly so in all the radial position, there might not be any spiral shocks. So in specific radial ranges, there might be spiral shocks present in the accretion disks. So here, that's why we have investigated this accretion flow changes at different radial distances. So now here we try to calculate shock strength from our model. So here we basically plot in this panel A. This is basically the spiral shock binary mass ratio. This one is the shock strength. This shock strength is defined as the ratio of the post-shock Mach number to the pre-shock Mach number. And this is the dissipation of angular momentum in the RM dot that I already mentioned how to calculate this RM dot from our model. So for this case, we can see RM dot is decreasing if the binary mass ratio increases. So that means if mass is increasing, so Q also increasing. So that means the gravity term for or the tidal force to the secondary mass is increasing. So that's why RM dot, the mass outflow rate, decreasing here. Also, you can see the similar kind of trend for shock strength and the dissipation of angular momentum, because if there is a strong shock present in the accretion flow, there will be higher dissipation of angular momentum in the flow. So we can also see for shock strength as well as the dissipation of angular momentum from our model. So there are some other flow variables that I have kept fixed for this calculation. So now let me describe. So here we want to focus for this accreting white dwarf in a binary. So we know white dwarf is basically the common endpoint of the evolution of the stars. And this white dwarf, accreting white dwarfs, they form in a binary, co-evolve with the into the interactive state composed of an accreting white dwarf and a normal star filling Roche lobe. So this normal star may be the main sequence star, or the means the red giant, or maybe the red giant. And this accreting white dwarf, they can accumulate this material through this accretion process, and if this accretion process continues, so this mass can reach the white dwarf mass can reach Ashokal limit, and it can explode, and which is known as the supernova. So this kind of system is known as type 1a supernova. Also, this type of progenitor channel is also known as single degenerate channel. Okay, so I will be apply our model to a particular particularly this single degenerate channel. So before going to the plot, I want to discuss some of the thing that it is very important, that in white dwarf study of the studies are there to investigate the evolutionary states of this progenitor supernova type 1a. And in this work, we apply our model of this single degenerate channel to exhibit the mass outflow or the calculate the mass outflow. So for that, we analyze the parameter space basically in terms of the orbital period of the secondary mass, that is capital P. This is not the pressure, this is the orbital period. So orbital period we can calculate by using the angular velocity of the binary, and this is m, which is this type of relation is generally used in the progenitor studies of supernova type 1a. And also we calculate the total mass outflow rate from a model in every point in the parameter space using this relation, where this RM dot is calculated at position R. This is position R2, this is position R3. So we can calculate the total RM dot using this relation. So here we basically calculate the parameter space in terms of the secondary mass and the orbital period of the binary period in days. And here we also fix various primary white dwarf mass. This is white dwarf mass 0.2 solar mass. 0.6, this is 1, this is 1.2. So we can see from here all the cases the parameter is shrinking, and if the mass white dwarf mass is increasing, we can see the parameter space increases. So what are the conclusion we can draw from here? That so we the mass outflow region increases with the white dwarf mass that I already mentioned. So that means the high mass white dwarfs undergo mass outflow more easily than the low mass one. And also we can see from here the for all the cases we can see the maximum outflow rate is happening when the secondary mass is low. So that means the tidal force is low. So mass loss increases in the disk when the gravitational binding energy weakens for the in presence of companion energy. And also from this calculation, we can see the maximum outflow rate is lies within the range from 15 to 50% from our calculation. So this is basically our accretion ejection model in presence of spiral shock for accreting white dwarf. So now we want to extend this model to apply for the spiral galactic disk. So we know the spiral galaxy is very common in the universe. So this is an spiral galactic image, NGC 3938. So in this type of accretion or the spiral galactic disk, we can apply our model as well. So for this spiral galactic disk, we need to know various observational parameter. One is called the shear rate. Okay, so shear rate is basically defined like this. This is basically the V phi is basically the azimuthal velocity, and R is the distance from the center to the spiral arm. And also we need the pitch angle. It is basically defined as the tightness of the spiral arm. So that means if pitch angle is higher, that means it is loosely bound of the spiral arm, and if pitch angle is lower, that means it is tightly bound. So for galactic disk, we need self-gravitating force, because this is the mass of this accreting disk is not means comparable to the center of this galaxy. It is almost comparable, or maybe very close to this center object. So we cannot ignore the gravity effect of the accretion disks. So here we need to consider the self-gravitating force in our model. So here we consider force based on this is Mestel 1963 prescription. And also for this galactic disk, it is believed that these spiral shocks are basically forming in the galactic disk for this spiral galaxy. And in this spiral galactic position, there might be the star forming region. So in our model, we assume that the mass basically event star formation rate. Obviously, there are some other maybe other reason is there to forming this star. But in our model, we solely consider that the spiral arm and the spiral shocks may causes the star forming region or the star formation rate. So if we calculate the m dot out from our model, we can predict rate or the star formation rate for this various spiral galactic disks. So briefly, I want to preliminary, there are some preliminary results. This work is going on. So I want to show the effect of gravity, self-gravity in the accreting disk. So here we consider the spiral, the self-gravity, and dotted region is dashed region is for non-self-gravity consideration. So here we can see for a particular input parameter, that means the flow parameter as well as the adiabatic indexes, if we fix, then there might be no shock in non-self-gravity disk, but for self-gravity disk, there might be a spiral shocks present in the disk. Okay, so you can see two spiral shocks is forming here, and for non-self-gravitating disk, there is no shocks. So also another important aspect, we are analyzing theory in observation as well as in various simulation. Already people showed that there is a strong correlation between the pitch angle and the shear rate. So here we basically calculate the shear rate in terms of this azimuthal velocity. Okay, so this correlation. So here we also try to calculate the correlation between the pitch angle and the shear rate. So for that we calculate spiral shocks. So here we basically vary three different density profile or the input density in the accretion disks. So you can see with the increase of density in the disk, the shock forming region is reducing for all the cases. And also for all the cases, we can see there is a correlation between this pitch angle and the shear rate from our model. So this kind of study will help to understand what are the correlation or between the speech angle and the shear rate from our model. And based on that, we also try to calculate what are the star forming rate that I already mentioned for various spiral galaxies. For these galaxies already the speech angle and the shear rate already it is observed or measured for various spiral galaxies. So using these two quantities, we can calculate what are the star forming rate, or also we can predict what are the star formation rate for various galactic sources, especially the spiral galactic sources. And for this source, I can remember the pitch angle is around 16.9 or something degree, and shear rate is 0.74. So already I have calculated this one, the m dot out or the star formation rate for this particular galactic source, or for the particular this spiral galaxy is around 10 solar mass per year, the star formation rate. So now I am doing this calculation. It will take some time to tabulate all those galaxies, the pitch angle and the shear rate. Based on this pitch angle or shear rate, I want to calculate what are the star formation rate based on our accretion injection model. So maybe
Ramiz,
I should end here.
Ramiz.
Yeah.
Oh, okay, you finish. Okay. So actually, I have a
so
question.
maybe I should end here and yeah.
Go ahead.
Please.
No, you go ahead.
No, I should stop here. Yeah.
Okay.
I already finished. Yeah.
Okay, so let's thank Ramiz for this wonderful talk about his work. And now he's open for question and answer. So kindly unmute yourself and ask the questions or raise your hand. So in the meantime, I can go ahead with the question that I'm asking. So you said something that you have want to tabulate some of the sources, and for that you are calculating. So how many sources you have?
Already I have sampled around 79 spiral galaxy. It is
Okay.
taken from Califa.
I think I don't know, my internet is also probably breaking. So what did you say?
Yeah, so so already I have taken 79 spiral galactic sources. It is taken from Califa database.
Okay, Califa. Okay. So the star formation rate that you are putting here, you are calculating from the shear rate and pitch angle.
Yeah, so basically the shear rate and pitch angle is already observed for this 79 galactic sources.
And how did you calculate this
so
star
from there? Yeah, so basically I am telling that. So pitch angle in our model, I already mentioned pitch angle is very important. So I can show you here. So if particular spiral galaxy, the theta is known. Also from shear rate, we can calculate what is V phi, the azimuthal velocity. Okay, so in our model, we need this theta and also this Q2. Q2 is basically the V phi. So from there, we can easily calculate, is there any spiral shocks in our model? And if there is a spiral shocks, we can calculate what is m dot out. Because m dot out, the mass is ejected from our model due to the spiral shocks.
Okay, so the outflow rate or star formation rate that you are, it's an input parameter for your model, right?
Yes. This theta, this pitch angle, and the shear rate.
And how do you get the star formation rate? Is it based on H alpha line, or how do you get?
No. It is purely from. So means if we input these two parameter from there, from our model, we can easily calculate what is this height, this density, and all those things. Yeah.
And have you compared this m out dot equal to the star formation rate that you are mentioning? So have you compared it from observations?
Observation for I can say for this particular NGC 3938. Star forming rate around say around 5 or 6 solar mass per year, I guess. So we are getting around 10 or something like that.
Okay.
Yeah. So I have to check. Means this is a particular observation. So I have to look for other observation as well.
Yes. Okay. Any further questions from anyone?
Maybe any discussion suggestions are always welcome. So I am also new in this field. So if any suggestion, discussion, I will happy to share with you.
Okay, so the spiral galactic disk, this work you started recently, and that previous work that you have did.
Already this work I have already published. This
okay.
Around this white dwarf in a binary.
Okay. And so what is the reason of this discontinuity? There was one slide I forget. There was talk was this one. No, the next one.
So maybe I should explain the spiral shocks, forming of these spiral shocks. You mean this one?
No. There's
this one.
4. No, you went 2 ahead. I think.
Okay. Let me stop then. Where? This one? Yeah,
this one. So this A and B, the plot, A and B panel, the left side, on the left side.
Yes.
So this discontinuity is mostly, I mean, the reason of this discontinuity?
Reason due to the spiral shocks is forming here, because you can see it is dependent on the flow parameter as well as the binary parameter. So you have to choose the flow parameter as well as binary parameter accordingly to get the shock. So at this shock, there might be there has to be mass conservation and also the momentum conservation, also the energy conservation. So if these three conditions is satisfied there, so there will be a discontinuous transition.
Okay.
The reason is that there is presence of this tidal force due to the secondary star.
Okay, so if there are no further questions or comments to Ramiz, then let's thank again him. And Ramiz, probably people can discuss with you since you are here also separately. Okay, so thanks for the presentation.
Thanks a lot.
Okay, so with this, we'll close for today and we'll meet again probably next week.